All right, everyone, we are ready for the final. So I am going to work my way through this whole practice exam from start to finish. All I have here is my calculator, and I have the same equation sheet from the midterm equations, charts, periodic table, etc. So let's open the periodic table. Okay, so let's go ahead and do it. All right, so first up, assuming equal concentrations of conjugate base and acid, which one of the following mixtures is suitable for making a buffer solution with an optimum pH of pH 9.2 to 9.3? All right, when I think about buffers, I know they work best in a pH range of plus or minus 1 from their pKa. I have Kas, it looks like, except for this one. I don't have a Ka for this one because this is not actually a buffer. I know that because HCl is a strong acid. Maybe I should check if the rest of them are buffers. Let's see. So this is a weak acid with a conjugate base bonded to a metal. Same thing here. Same thing here. All right, so, oh, and this one. This is one, it's a little different because it has the chlorine, but yes, it is plus or minus 1 hydrogen of each other. So this looks good. These are all buffers except for that D. So I'm going to figure out the pKa for each one. And remember, that's just minus the log of the Ka, so grab my calculator. All right, so there's my pKa's. I'm looking for something in the 9.2 to 9.3 range, so I see that must be this one with a pKa of 9.25. All right, arrange the acids H2Se, H2Te, H2S in order of increasing acid strength. It's more light here. Let's see if that's better. Okay. So it's a little more focused. All right, so I'm going to find these elements on the periodic table, and I see they're over here in a column. So I'm looking for 2 hydrogens bonded to each of these things. And the thing I know about a strong acid is a strong acid will easily lose its hydrogen, right? That's what makes something a stronger acid, is it's going to lose its hydrogen. When I think just about the size of these guys or their electronegativity, I know this tellurium is most likely to lose its hydrogen, right? The hydrogen's far from the nucleus, it's not very electronegative, versus the sulfur should be more electronegative and smaller, so it's closer to the nucleus. So I think tellurium should make the strongest acid, sulfur should make the weakest. And when I look at my choices, let's see, there's sulfur, and there's tellurium, so that looks like my best choice. All right, for this zinc blend structure, ZNS relative, edge length. Okay, determine the density. All right, so remember, density is mass divided by volume. For my mass, I have Zn and S, zinc 65.39 and sulfur 32.07, so 97.46. That's how many grams are in 1 mole. What I want to know, remember, is grams per unit cell. So I'll convert that. First, I'll convert 1 mole to 6.022 times 10 to the 23rd atoms. And then I need to know, let's see, face-centered cubic. Okay, so face-centered cubic means there are 4 atoms per unit cell. So 4 atoms, 1 unit cell. So I can figure out the mass of my unit cell here. All right, so there's my mass of the unit cell. Then I need the volume of my unit cell. I have the edge length. Remember, if I had the radius, I'd have to convert to edge length, but if I already have the edge length, I can just cube it. since all of my densities are in grams per centimeter cubed, I'm going to want to convert my picometers to centimeters. I'm going to do it before I start. You could do it at any point, but 540.9 picometers I'm going to use that conversion factor, but there are lots of ways you could think about converting that. So that's just my edge length in centimeters. And then for my volume, I will cube it. Probably should have kept more sig figs since I had 4 sig figs. All my answers have 4 and I rounded to 3, but oh well, we'll go with it. Hopefully I'll be close enough that I can pick the right answer. All right, so 6, okay, that's my mass. Here's my volume. All right, so I got 4.088 grams per centimeters cubed. That's pretty close to 4.091. Like I said, I did drop a sig fig where I probably should have kept one, so call it good enough. All right, next up I have a phase diagram. So I need to label my phases on my phase diagram. I like to think about it, if I were to have it at low pressure and I continually just heat, eventually it would become a gas. If I have something cold and I put it under high pressure, eventually it would become a solid, and then the liquid would be in the middle. So in this case, it's asking just for A, and so that should be a solid. All right. The graphs below all refer to the same reaction. What is the order of this reaction? Okay, so all I care about is which one has a straight line, which is this one. And then remember, each of these correspond to a different type of reaction, a different order of reaction, and the one that's the straight line is the answer. So if it's natural log, that was a first order. This is the order we learned them in. 1 over was a second order, and then if it was just the concentration, that was a 0th order, and since that's the one that's a straight line, that's my answer. This is a 0th order reaction. Only one of them can be a straight line. Whichever one is a straight line, that tells you what it is. All right, in the coordination compound of all of this stuff, the coordination number and the oxidation number of the metal atom respectively. Okay, so coordination number I can count just by looking. So I've got an ammonia, I've got a chlorine, and I've got 2 ethylene diamines. Remember that the ethylene diamines are attached twice. They're the ones that attach twice. So I've got 2, 4, 5, 6. So the coordination number is 6. And then I can figure out the oxidation number of either 3 or 4, hopefully. Remember that I can, like, basically think of it lots of different ways. But anyway, I'm going to think about it like the anion is -2 because there's 2 bromines, and so that means the whole cation must be +2. Then I can look at individual ligands. Ammonia is a neutral, ethylene diamine's a neutral, chlorine's a -1, and so the chromium must be a +3 to make it equal +2. All right, kinetics, reaction order with respect to fluorine. All right, so I'm going to pick 2 experiments where the ClO2O is staying the same, but the F2 is changing. That looks like 1 and 3 to me. You may have done this enough that you can just sort of look at the change and see what it is, but I'm going to write it all out. Remember, the rate law for a reaction looks like rate equals rate constant times reactants raised to unknown stoichiometric coefficients. So that's what I'm going to plug into. I'm going to do number 3 first since it's the bigger rate. So number 3, I get 1 times 10 to the minus third equals k times 0.1 to the x times 0.01 to the y. Do the same thing for number 1. Cancel. I didn't include my units here because those would cancel, but they have units. But anyway, when I divide, that comes out to 2. Remember, for the exponent, you divide the number, keep the exponent, so 2. So x must be 1. All right, next up, what is the freezing point of a solution prepared from 50 grams of ethylene glycol and 85 grams of water? The Kf of water is 1.86 degrees Celsius per molal. Remember that the change in freezing point is Kf times m. The actual freezing point would be the freezing point of pure water, which is 0 degrees Celsius, minus the delta Tf. So whatever my change is, so I just have to figure out my change. My Kf I know. My molality I need. Molality, remember, is moles of solute divided by kilograms of solvent. So I know, if I didn't know what my solute versus solvent was, the fact that I have more water means that's my solvent. Also, it told me the Kf of water, that's for the solvent, so. All right, so that's how much water I have, and now I need to convert my 50 grams of ethylene glycol to moles. I'll use the molar mass. All right, 2 carbons, that's 24. 6 hydrogens and 2 oxygens, so 62. Oops. All right, so divide. This is a pretty big molality compared to what we're used to, but when you look, there's almost as much ethylene glycol as there is water. It's all, it's not a 50-50 mix by mass, but it's not that far off either. So I'm not too surprised that it's big. I'm going to plug that in up here. My molalities will cancel. All right, so that's my change in freezing point. Remember, I need to subtract that from 0. So it's going to be negative 17.6. All right. Consider a 0.9 molar aluminum nitrate solution. The solution has a nitrate concentration of. Okay, so this is just asking me how this will separate. So remember that the aluminum will be one part of it, and then the nitrates will all separate from each other. So if I had 0.9 molar here, I'll have 0.9 molar here, and 3 times that for this one, right? Because there's 3, and so it will be the 2.7. All right, the correct formula, dichlorobisethylene chromium 3+ ion. All right, so I see 2 chlorines, and the bis, remember, means 2, so 2 ethylene diamines, so I can kind of look at my choices. There's one that's not right, and there's one that's not right, because those didn't have the right number of ethylene diamines, so it's one of these. So all I need to figure out is the charge of the whole ion Remember that chlorines are -1, and there are 2 of those, so that's a total of -2. Ethylene diamines are 0, and the whole thing, and the chromium, is +3. So the whole thing has to add up to that, so that's 1. All right, electrolysis. Current of 0.8 amps was applied to an electrolytic cell for 2.5 hours. Calculate the mass of cadmium. Remember that for electrochemistry, you can either start from mass or you can start from amps times seconds. I have amps times hours, so I am going to go ahead and convert those to seconds by multiplying by 60 to get it to minutes, and then 60 again to get it to seconds. So now I have amps times seconds. Once I have that, I'm ready to use Faraday's constant to convert to moles of electrons. Then I need to go from moles of electrons to moles of stuff. I can see this is cadmium 2+ because there's 2 chlorines attached to it, becoming cadmium. So 2 moles of electrons for every 1 mole of stuff. And then I need the molar mass of cadmium, 112.4 grams to get to moles. You could break this into steps, but that's all in one go. And I just need to put it in my calculator. 0.8 times 2.5 times 3,600 times 112.4 divided by 96,500 and divided by 2. In 2.5 hours. All right, let me put it in my calculator again. Okay, I don't know what I did the first time. Maybe you saw it when I put it in my calculator wrong. I obviously put in a calculator error. I just put the same numbers in again, and I got 4.2 this time. So I get A, which is the correct answer. I don't know what I did the first time. My setup was correct. All right, next up, calculate the E cell for a silver and aluminum cell in which the cell reaction is this. Okay, so I know I need to do cathode minus anode. If I was not given a balanced equation, I would say the bigger number is the cathode and the smaller number is the anode, and I would do 0.85 minus a negative 1.66. But I do have a reaction, so I want to do it the way that the reaction is written. And in this reaction, it looks like silver is being reduced, which is the cathode, which means the aluminum is my anode, which means what I said was correct. That's my cathode minus this. But again, I'm doing it because that's what the reaction says to do, not just because that's the bigger minus the smaller. So when I do that, I think I should get 2.51 volts. Which of the following substances is expected to have the highest boiling point? Remember, highest boiling point is based on intermolecular forces. I know these are all polar molecules, but only one of them does hydrogen bonding, and so that would be the one with the highest boiling point. There we go. Solubility of CO2 gas in water is not dependent on pressure, increases with increase. Okay, so let me just think about it before I read all these choices. I know, this is how I remember it, honestly. I remember that solids are more soluble at higher temperature and gases are less soluble at higher temperature. Okay, that doesn't work. All of these are about pressure. But I know that they should, well, okay, so then I know they should increase with increasing gas pressure. That one I do know. Also, if I look at these, I do think there should be a pressure dependence, so that doesn't make sense. And then look at, these are basically the same, right? Increases with decreasing gas pressure should be the same as decreases with increasing gas pressure. That just means they're opposite. So the only one that really makes sense is B, and that is the correct answer. Equilibrium constants, remember that pure liquids get left off of equilibrium constants, just aqueous and gas get included, products on top, reactants on the bottom, stoichiometric coefficients become powers. There are none, so let's see, I need H2CO3 on top, which is that and that, but I don't want water, so that just leaves me with A. Which of the following, okay, for the following reaction at equilibrium, which of these would cause the concentration of Br2 to increase? All right, so that means, that's another way of saying shift to the right. Which one of these should shift to the right? All right, so if I remove some NO, that right away sounds like yes, that would shift it to the right. So that sounds like a good answer to me. Compress the gas mixture into a smaller volume. All right, so I have 2 moles of gas on the left, 3 moles of gas on the right, so it would shift toward the side with less gas. That should shift to the left, so that's not it. Lower the temperature. I see that this is an endothermic reaction, that delta H is positive, so I'm going to write heat over here. And so then if I lower the temperature, it should shift back toward the left, not it. Remove some NOBr, that's my reactant, remove this, it would shift to the left, so that's not it, so only A. All right, POH is 9.6, what's the hydrogen ion concentration? You can do this a few different ways. I'm gonna start by figuring out the pH, which is 14 minus 9.6. Because it says hydrogen ion, right? So I need the pH. So then it's 10 to the negative 4.4. I got 3.98 times 10 to the minus 5. So that looks like E. All right, delta G. Okay, delta G is just products minus reactants, multiply everything by their stoichiometric coefficients. So starting with the HNO3, 2 of those, 1 NO, I like to label things so that if I'm making a mistake, if my answer doesn't turn out right, I can more easily check my work, but otherwise you don't really necessarily need to. All right, 3 of the NO2s. And then so that's NO2 and 1 water. All right, so as long as I put this in my calculator carefully, I should be good to go. All right, so I'm going to do 2 times negative 79.9 plus 86.7. I'm going to distribute this. Yes, I'm going to do minus 3 times 51.8. And then distribute that, that'll be a plus 237.2. 8.7. I didn't include any units, but it's kilojoules per mole because that's what these are in, so that's what my answer would be in. All right, complete and balance the following redox reaction. What is the coefficient of I minus when the equation is balanced with the smallest set of whole number coefficients? Okay. I need to start with half reactions. So I started by separating my manganese into one and my iodine into the other. Then I need to balance oxygen with water. Oh, first I balance anything that's not oxygen or hydrogen, but there's just one manganese in each, one iodine in each, so that's good. Then balance my waters, 2 H2O down here, 3 H2O down here. Balance my hydrogen with H+. Like that. And then balance my total charge with electrons. So I've got 3+ over here and 0 on the right, so I need 3 electrons on this side. I've got 1- over here. I've got 5 pluses over here. Right, 5 pluses. Okay, I have to think this through here. 5 plus and 1 minus. So I need to bring this down to -1 with 6 electrons to make that both -1. Now I need to make the electrons cancel. Let me just grab a different color so I can keep going here and not rewrite it all. So I'm going to multiply this through by 2 to make 6 electrons and 6 electrons. So this would be 6, 8. Normally I would probably rewrite this, but just to keep it all together on the screen. And then I can add it up. All right, so the electrons are gone. All right, one more time, one more new marker. Electrons are gone. We've got 8 hydrogen over here and 6 hydrogen over here, so that would be 2 H+ over here. The waters will end up over here. All right, so 2. And then my waters, I got 4 on the right and 3 on the left, so that's just 1 over here. Over here. All right, I want to check if it's balanced. Right now I have 2 hydrogen, 2 hydrogen, 2 manganese, 2 manganese, 8 oxygen. I've got 3 plus 4 plus 1 is 8, 1 iodine, 1 iodine, a total charge of -1 over here, total charge of -1 over here. So this is balanced. It is not in basic solution. I actually can stop here if I want to because it's asking for iodine. Changing this to basic solution is only going to change the hydrogen and the water. So my 1 here is still going to be true. But just to remind you of how I would change it to basic solution, remember I need to get rid of all the hydrogens by adding enough OHs to get rid of the hydrogens and do it to both sides because now we're balanced, so we want to do anything we do to one side has to be to the other. This would become 2 waters, and then that would cancel with this water. So it would be 1 water, this is gone. Like that. That would be my actual balanced equation in basic solution. All right, molar solubility of magnesium carbonate is 1.8 times 10 to the -4th. What is the KSP? All right, magnesium carbonate should look like this. I know magnesium from the periodic table is a +2, carbonate is a -1. So my reaction, my equilibrium would be it separating. Into one of each. Excuse me. And then remember that would be like -x and +x and +x, x and x. Remember that x is the molar solubility. So this is, I know this is getting kind of messy because I didn't get another piece of paper, but this is the molar solubility. So this is my x. So when I go to calculate my KSP, which would be x squared, it would just be that number squared. All right, number 21, 9.5% by mass, acetone, density, what is the molarity? So for molarity, I need moles of acetone per liter of solution. I'm going to assume I have 1 liter of solution, so that's done. For the acetone, for the moles of acetone, all right, so now I'm going to have to use some of my other information. I have my 1 liter, so I can figure out from the density. My total mass. Now, if this feels like it's a little different, each one's a little different, it is. So I'm just using what I've got, right? Like if I have a volume, which I do because I assumed 1 liter, and I've got something that includes volume, I can just kind of go with it and see, well, what can I get? I can get this. What can I do with that? Well, I know 9.5% of that is acetone. Oops, 0.095 when I change the 9.5% to a decimal. Oop. This is per milliliter. Did you catch me there? That was per milliliter. I have 1,000 milliliters, so I have 984.9 grams. Whoops, there we go. So 984.9 grams total. 95% of that is what I have. Okay. So 93.5. That's my mass of acetone. I need moles of acetone, so I need my molar mass. 36 plus 6 plus 16 is 58. 1.61. And so 1.61 divided by 1 is just 1.61. All right, the reaction, blah, 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 is expected to be second order. Which of the following kinetic plots would be the most useful to confirm whether or not the reaction is second order? So we talked about this on page 2. Remember we made these plots? All of them were versus time. I think that's one of the variables. Nope, they're all versus time. Okay, so that's good. And then the plots are the only ones I care about ever. Natural log, A, and 1 over A. So anything else. So here's the concentration versus time, that's 0th order. 1 over, that's second order. Natural log of 1 over, that's not a thing we talked about. NO, or whatever the thing is, NO2 in this case, squared, not a thing we talked about. Natural log of concentration, that's first order. So C and D are never going to be correct. And this is asking about second order, so that would be B. All right, here's some data, and I want to figure out the NOBR when it reaches equilibrium. So I don't want to use this because it's kind of, well, I guess I can. Let me just write it in 2, 1, and 2. And put my arrows in so I know where to subtract. So this would be minus 2x, minus x, and plus 2x. And I can see that 2x is equal to 0.5. And since I just want NOBR, I can just add 0.5 here for the change, and I should get 1.5 for equilibrium. Right, I hope that makes sense. So because it was 2x and this was 2x, I know that the x must be 0.25 or 2x is 0.5, and so. All right, conjugate base of an acid is just the exact same thing minus the hydrogen. If it was neutral before, now it should have a negative sign, so that would be this. You can see some of these take a long time, some of these are pretty short. Make sure you are not wasting time on the ones that are easier and shorter, but not rushing yourself on the ones that are longer and need more time. All right, which of the following will have the lowest pH? First of all, let me think about what lowest pH means. It might be easy to think lowest pH, least acidic. That's not true, right? Low pH is most acidic, so just think about what it's really asking. When I look at these, what do I see? I see a salt, a neutral salt, in fact, a base, a weak acid, a strong acid, and a weak acid. So most acidic, I don't have to do anything else other than identify that that's a strong acid, and of these choices, that would be the most acidic. They're all the same concentration. All right, balancing a nuclear reaction. So remember, I want the bottom total to add up on both sides and then the top total. So 94 on the left, and right now I just have this 38 on the right, so I need 56 on the bottom. I can check my periodic table and see that 56 is barium. So I can probably almost pick the right answer. It's not that, not that, not that. And then on the top, all right, so I have 239 plus 1 is 240, minus 91, and then there's 3 neutrons, so that's minus 3, and I get 146. All right, coordination compound, coordination number and oxidation number again. So now this time I have 2 amines and 2 chlorines, so that's only 4 attachments, so the coordination number is 4. I have ammonia is a neutral ligand, chlorine is a -1, so that's a total of -2. The whole thing looks to be neutral this time. Normally they're an ion, but this time it's neutral. So I need the platinum to be +2. For which type of titration will the pH be basic at the equivalence point? So I need basic to win. That sounds like a strong base with a weak acid. Remember, if it's a strong base, strong acid, it should be exactly 7. If it's going to be basic, it needs a strong base. Which of the following mechanisms is consistent with the observed reaction order? Okay, and what it says about the reaction order is second order with respect to NO2 and 0th order with respect to CO. So NO2 squared and no CO at all. So in my slow step, that's what I need. I need CO not to be there and NO to be 2 times. Slow step, I see NO2, sorry, not NO. But I see CO, so that's not it. Slow step, 2 NO2s, that sounds like it. Slow step, N and NO2, not it. Slow step, NO3 and CO, not it. All right, potassium and then this iron cyanide thing. All right, how many unpaired electrons does iron have? Cn- is a strong field ligand. So I need to use this to figure out the charge of the iron, to figure out how many electrons I even have. These are -1s, and there are 6 of them, so that's -6. Potassiums are +1, and there are 4 of them, so that's +4. So my iron must be +2 to make that come out neutral. It's a strong field ligand, which means a lot of splitting between the 2 levels. So when and then how many electrons does iron have? All right, so iron neutral would have the noble gas, and then 1, 2, 3, 4, 5, 6, 7, 8. I'm taking off 2 of them, so I would have 6 electrons. It's strong field, so they stay low. 1, 2, 3, 4, 5, 6. No unpaired electrons. All right, charcoal found under a stone at Stonehenge is carbon-14 activity that is 0.6 that of new wood. How old is the charcoal? If it has more than 50%, then it hasn't made it to a half-life yet. Like, I don't think I really need to do a calculation here. It still has a higher activity than it would after one half-life, so it must be less than one half-life. You could actually do the calculation if you want the equation. It would be that, and you'd put in 0.6 here because it'd be 0.6 and 1. Right, like whatever amount you have here, it's 0.6 of that here, so that would be that. And you could actually figure it out, but I think you would get an answer less than 5,730 years. And I don't think I actually need a calculation. Which one of the following substances should exhibit hydrogen bonding? We talked for a second about hydrogen bonding earlier, but remember it's NO and F. So let's see. Sulfur, carbon, silicon, hydrogen only, none of those have it, but we've got this N bonded directly to hydrogen right here. All right, the number of atoms in body-centered cubic. We did an example where we used this fact earlier, but remember, a simple cubic is 1. Body-centered is, oh yeah, we used face-centered earlier. Body-centered is 2 because that's 1 in the middle. And then the 8/8 on the outside, and then face-centered is what we did, which is 4. Which of the following liquids would make a good solvent for iodine? Remember, like dissolves like. I see this as two things bonded to, like the same thing, like something bonded to itself. So this would be nonpolar. So I'm looking, polar. So I'm looking for something nonpolar, no hydrogen bonding. I see that should be hydrogen bonding, that looks polar, hydrogen bonding. I don't 100% necessarily know, but that looks like it could be linear. Definitely doesn't have hydrogen bonding. All the other ones look like clearly not, so I'm gonna go with that one. And it is linear, and it is nonpolar. Appropriate units for a first order rate constant. If you don't know this, then write a rate law. For a first order reaction, solve for the rate constant. Oh, whoops, sorry. Okay, write the rate law. Solve for the rate constant, like I said, but not what I did. There we go. And then write in the units. So the rate would be molarity divided by seconds, and then the concentration would be molarity. So those would cancel, and you'd have 1/seconds. Or you could just memorize that. That is the unit for a first order rate constant. All right, what is the hydrogen ion concentration when the KOH is this? Remember that if KOH is this, then OH minus is this as well, because it would separate into 1 potassium and 1 hydroxide. And so I can figure out H plus is 1 times 10 to the minus 14th divided by, let me just remind you, KW is the 1 times 10 to the minus 14th, and KW equals H plus times OH minus. So I'm just solving for H plus by taking KW divided by OH minus. All right, calculate the pH of a buffer. Remember that there's an equation for that. pKa plus log of base over acid. pKa is minus the log. I don't have the pKa, so I need it minus the log of the Ka. My base is the sodium benzoate, and my acid is this benzoic acid. That should be 9.7, I guess. Right? 5 should round up, and okay, that's the answer. Which of these species would you expect to have the lowest entropy? Remember, gases have the highest entropy. There are lots of gases here. There's a liquid here. Solids have the least entropy in terms of phases, and so that's what I would pick. We could also start looking at I guess in this case, yeah, just the phases here. Solids are the most ordered. All right. I've got a delta H, I've got a delta G. What minimum temperature will the reaction become spontaneous under standard conditions? Remember to find where it switches spontaneity. I want to set delta G equal to 0, and then I want to solve for temperature. I have the delta H, but I don't have the delta S. So what I'm going to need to do first is use this equation. T delta S, there we go. And use the delta G and the delta H to solve for delta S. And then I'll plug in over here with delta S. Okay, let me show you what I mean. All right, so I plugged in my delta G for delta G, delta H for delta H, temperature in Kelvin, and I can solve for my delta S. All right, so I need to minus 33.1 minus 128.9, subtract that to the other side. All right, so I subtracted this, 33.1 minus 128.9, that's where I got that. This negative is still here, 298. So now I'm going to take this number and divide it by negative 298. And I get this. And the unit would be kilojoules mole Kelvin. Now, if I was reporting a delta S, I would probably convert it to joules. That's what we normally do. But because I'm going to use it again, I'm just going to leave it in kilojoules, because then I always just have to convert it back anyway. All right, so that's my delta S, and this is my delta H. For when I want to do this, set my delta G equal to 0, that's where it switches spontaneity, and solve for temperature. Let me just solve this first by just like adding. All right, so what I need to do is delta H, 128.9 divided by delta S, which I already have in kilojoules, so I don't have to convert, but if I didn't have it in kilojoules, I would convert. That's where that Kelvin comes from, so I'm going to divide this, 128.9 divided by 0.321. Got 401, or 402, and then the unit would just be Kelvin, which is one of my choices. All right. So here it's telling me what my anode or what my electrodes are, and not which one is which. It gives me the E cells. It's not asking me to calculate an E cell, but what I can figure out from this is that whichever one is bigger, this should be the reduction, and this one should be the oxidation. Right? Whichever one would have been higher on the table would be the reduction, would be the cathode. This is the one that would be higher on the table. So now I want to keep this one as a reduction, but this one I want to flip and make it an oxidation. And then in order to add it up and make it balanced, I need to make the electrons cancel, so times 3 and times 2. And so I can see I should have 3 Pb2 plus, 2 aluminum, 3 Pb, 2 aluminum, 3 plus. It looks like A. You could write all those steps out if you can't quite see it yet, or you can do like what I did earlier, and like write them in. Whatever you want to do. Okay, pH of a weak acid. I do need an ice table for this. Point 0.05500 minus x plus x. And then remember K equals Ka equals H plus, or A minus, for HA. All right, so put my Ka in, I've got x squared on top. Assuming x is small, I've got 0.0055 on the bottom. So that's my number, square root of that. And then pH is the question, so minus the log of that. Sorry, I got minus the log of it, 3.327, so 3.33 for that. All right, calculate the potential for this cell, which is not in standard conditions. So let me just make sure I know what's going on. I've got copper being reduced, and nickel is being oxidized. I will need the E cell standard, which is cathode minus anode. Cathode 0.15 minus anode is negative 0.25. I think I can do that one in my head, but I'm going to double check my calculator. Minus negative 0.25, and I get, yeah, 0.4. All right, so that's E cell standard. E cell, let me just pull out my equation sheet so we are all looking at the same thing here. I'm going to go ahead and use this one, I guess. These are both the Nernst equation, just different forms. This one has constant plugged in, this one doesn't. This one's natural log, this one's log. I'm just going to pick the one that has the constants plugged in, less places to make a mistake. So E cell equals E cell standard minus 0.0592, and that's the volts part, divided by N, log of Q. All right, so this E cell standard is 0.40 volts minus 0.0592 volts over N. N is the number of electrons that would cancel. In order to make these cancel, I would have to multiply this one through by 2, and then the 2 would cancel, so that's what I put there. And then log of Q. Q is products on top, reactants on the bottom, raised to stoichiometric coefficients. All right, I don't have room for this, so let me do it down here. So Q, let me just write it out, would be nickel on top, copper plus squared on top. It's out of the way, sorry. There we go. And then nickel solid gets left off, that doesn't get included, but copper 2 plus squared on the bottom. And now I'm going to plug those numbers in. All right, I'm gonna put it in my calculator. 0.01 squared. I didn't put in the 1 because that doesn't matter. So I get 10. For my Q, so I plug that in. All right, now I'm going to do log of 10 times 0.0592 divided by 2, and then 0.4 minus that. 0.37 volts. So definitely a few steps in this one. The Nernst equation is not the simplest equation, so be ready for that. All right, 43 Kc. Calculate the concentration of H2. All right. So it's an equilibrium problem. I'm going to write an ice table. Um, 0.55 moles per 2 liters. I need this in molarity, so 0.55 divided by 2. Right? No hydrogen, no iodine. And then I'm given the Kc. All right, so this is minus 2x plus x plus x. 0.275 minus 2x, x, x. All right, for my K, H2 and I2 on top, each I on the bottom, and it gets squared. I've got that. Remember, I don't have to assume x is small here. I can actually solve this exactly by taking the square root. Square root of 0.0156. All right, now I am gonna, let me get some extra paper for this one. I'm running out of room. 0.25, and this would be x on top, and 0.275 minus 2x on the bottom, because that's what the square root of those things would be. All right, so now I'm gonna go ahead and cover up all of this because this is all I need to do now, solve for x. Cross multiply. Distribute. You know, 125 times 0.275. Get the x's together. Remember, this is 1x plus 0.025, so 1.025x. All right, so 0.00336. That's my x. Whew. All right, so now I'm ready to, what am I trying to do? Calculate the H2 concentration at equilibrium. H2 concentration at equilibrium is just x, so this is at 0.00336. I do not see that as a choice. All right, so where did I mess up? Okay, I messed up way back here. I just checked some numbers in my calculator and it was here. There was I put an extra 0 right here. So there's my mistake. So that's the problem. So then let me go from there. 0.125 times 0.275 is 0.0. Okay, so then that would be that. Oh, and then this would be wrong too. 0.125 times 2, this would be 0.25, so plus. All right, so now I just changed all my 0.025s to 0.25s, and now 0.0344 divided by 1.25. Now I got 0.02575. All right, so that's a choice. That looks better. All right. Almost there, 44. Thanks for hanging in with me, for as long as you have at least. All right, pH of a solution with this many OH minus ions. All right, I'm just going to figure out the pOH. You could do this other ways. So really, oh, no, wait a minute. It's ions per solution, not moles per solution. Oh boy, I was going to plug it in like it was molarity, and I was like, man, that's huge. Okay, so that's not good. I need to use Avogadro's number. Remember, Avogadro's number counts electrons, atoms, molecules, or ions. Anything. How many moles is just like a counting unit. So I'm going to convert this, 5.3 times 10 to the 17th divided by Avogadro's number. (8.8 times 10 to the minus 7th moles. That looks like a more reasonable. And then per liter, right, because of that. So that is molarity. So now that's what I can plug in. Minus the log of that. That's the pOH, so then I just subtract from 14 to get the pH, so 7.94. All right, consider a buffer solution prepared from HOCl and NaOCl. Which is the net ionic equation for the reaction that occurs when NaOH is added to the buffer? All right, so remember, a strong base is going to separate. The only part we care about is the OH minus. It can react with either the whole acid here or just the anion over here. It would react. The base would react with the whole acid, and it would make water. The hydrogen would go over and become water and anion. Of course, the anion is OCl minus. So that's what I want it to look like. I need OH minus on the left, which means these are all out, and it would react with the whole acid to become water and OCl minus. All right, determine the equilibrium constant. If I'm given a delta G, I do have an equation on my equation sheet for that. Delta G equals negative RT natural log of K. All right, I need to get K by itself because that's what I'm solving for here. This one is solved for delta G, but I have delta G, so I'm going to get delta G, or get K by itself. All right, so I get that stuff together, and then I need to get rid of the natural log with the exponential function. So K is the exponential of negative delta G over RT. Negative of a negative would be a positive. R is the gas constant, 8.314, but remember that's in joules per mole Kelvin. I want it in kilojoules, so I'll convert. Celsius, 298 Kelvin. All right, I'm going to do my exponent first. 28.5 divided by 0.008314 divided by 298. And I just need the exponential of that. 9.9 times 10 to the 4th. All right, standard reduction potentials, which is the strongest reducing agent. Well, let me just look at these choices. So whichever one has the biggest number, this would be the cathode. And the smallest number would be my anode. They're not in order. So this one, the chromium, depends which way it goes. We're talking about strongest. This would be the most likely to be the anode or the oxidation. Reducing agent, remember that reducing agent means that when it's reduced, it causes something else to be oxidized. No, reducing agent means when it's oxidized, it causes something to be reduced. It is causing the reduction, so it actually would be the oxidation. So we're looking at the the cobalt, so it's one of those. It should be the reactant, which it doesn't look like that's a choice because cobalt 2+ is the reactant, but remember this would actually be an oxidation. This is complicated, looks simple, not that simple. This would be an oxidation, so it would actually have to be flipped, and this would be the reactant of the oxidation reaction, which is a choice. Not what I have. Oh, no, wait a minute. I didn't. Oh, my gosh. These are negative. Sorry. This is bigger. Same argument. Move it up to here. Right? Negative 7.4 is smaller than negative 0.28. Sorry. I said all of it about cobalt not noticing. Chromium would be the most likely to be the anode. Chromium would be the oxidation. Chromium, the metal, not chromium 3+. Now this time I did have both choices, but this is backwards from how the oxidation would happen. So it should be chromium that kind. Sorry. Whew. 50 questions is a lot. I'm getting tired. I'm messing up now. All right, osmotic pressure. Remember that was molarity times the gas constant times the temperature, and this one is kind of set up for us. That's not happened in a lot of these, so that's fun when we're getting to the end and we're tired. All I have to do is convert my 37, what's it, 310? Yeah. My temperature into Kelvin. Everything else cancels, just sort of setting it up, and I will get an answer in atmospheres. All right, 2 sig fig, 6.4. Back to solubility, we're looking for something that would be not, this looks like nonpolar. Be tetrahedral, all the bonds would cancel. This would be polar, polar, hydrogen bonding, well, hydrogen bonding here too, but this one looks nonpolar. And then finally, helium atoms do not combine to form helium molecules, yet helium atoms do attract one another weakly through the most weak intermolecular forces are dispersion forces. All right, that's it. It took me 110 minutes. Or an hour and 10 minutes, sorry, an hour and 10 minutes. So hopefully you got something out of that if you stuck through the whole thing. And good luck on the final. Let me know if you have any questions.